Hi students, welcome to today's lecture on compiler design. So in our previous classes, we have discussed about the first phase of compiler, that is lexical analysis in unit 1. Today, we'll start the second unit, which is about syntax analysis, the second phase of your compiler. If you look at the syllabus of second unit, it is all about syntax analysis. First, we will discuss about the role of a parser, the jobs done by a parser, and then the basic concepts required to design, to begin designing the parsers, which are context-free grammars, writing grammars, top-down parsing. Sorry, this is actually a mistake. Parsing it is, bottom-up parsing, and then introduction to LR parsers. We will begin designing from here onwards. Okay. So first we will understand the role of parser. What are its activities and what are the tasks done by parser. And then we'll discuss about some basic concepts of uh, grammars. Okay. The role of parser, as we all know, parser is the second phase of compiler. Right. The first phase is lexical analyzer, which takes the source program as input and produces a stream of tokens uh, to the parser based on the request given by the parser. Get next token is the request given by the parser to lexical analyzer. Then lexical analyzer generates a token, issues it to the parser, and this process will be repeated until all the tokens are given to parser. And what is the output from a parser? Parser generates a parse tree after taking all this stream of tokens. Meanwhile, for generating parse tree, it can interact with symbol table also for getting the information about the tokens received from lexical analyzer. Okay, so this is the basic view of a parser in compile design phase. The parse tree generated by parser will be given to the next phase of the compiler. Okay. Now let us go through in detail what are several things that are done by a parser other than building a parse tree. So the basic role of parser is receiving a stream of tokens from the lexical analyzer and producing a parse tree by using this stream of tokens. Okay, so that is the basic role of a parser. And then second task of parser is determining the structure of program from the tokens received and classify them into uh, programming language entities such as what kind of statement it is. Is it a declarative statement or a control statement or an operational statement and so on. So it identifies the type of statement also. And then based on the syntax of the type of statement, it reports syntax errors if any statement violates the corresponding syntax rules. Right? For example, if it is a declarative statement, the statement should be, uh, for example, say in C language, declaring an integer variable should be like int space a variable name. Right? That should be the structure of a declarative statement. Right? If any statement violates, if any declarative statement violates that rule, then immediately it produces syntax error. So you need to observe this name. Syntax errors are generated by the syntax analyzer, whereas lexical errors are generated by lexical analyzer. So you should understand the difference between lexical errors and syntax errors. Lexical errors are generated if tokens are not valid, if token does not belong to the language, whereas syntax errors are generated if any statement violates the syntax rules. Okay, that means the arrangement or the order of tokens. If any violation is done there, it will be treated as a syntax error. Then next task of a parser is it also interacts with error handlers and produces appropriate error messages to display to the corresponding programmer, so that he can understand what is the error type there and where exactly error happened, and he can take a necessary action based on this message. So this is an important role of parser, to interact with error handlers and generate the appropriate error messages. And also, it is important to generate all the syntax errors in a given program, right? To perform that, producing all the syntax errors in a given program, the parser should know how to recover from the error which is identified, because parsing will be immediately stopped whenever there is an error identified in the source program. But then how to produce the remaining errors, remaining syntax errors in the program? uh, by applying this error recovery strategies. We have seen some error recovery strategies in lexical analysis also, and there are some error recovery strategies followed by parser also. We will learn these things later in our discussion. Okay, and then this is a general parser's role to interact with the symbol table, so that it can get the information about any token if it is required. Right? For example, it can get the information of type of a data from a symbol table, because symbol table contains all the information about the identifiers, uh, keywords, operators, and all, which are stored by lexical analysis phase. So that information may be used by the parser in order to uh, perform its tasks. Okay, so these are overall tasks done by a parser. What are they? First and foremost task is production of parse tree from the stream of tokens received from a lexical analyzer. If everything goes right, this is the task done by your parser. And then it also identifies the type of statement based on the stream of tokens received. Another task is, if at all syntax violations are there, then it should produce syntax errors based on the violations done by the corresponding statements. Also interacts with error handlers to produce an appropriate error messages, and performs error recovery so that the entire source program is scanned for syntax errors, and also interacts with symbol table to uh, get the information about tokens. So this is about the role of parser. Right. So we'll talk about the design of parsers afterwards. But before that, to understand the design of parsers, you need to understand some basic techniques, some basic terminology, which is relevant to that design of parsers. That is about the grammars. The type of grammar used by parsers is context-free grammars. So why we need to learn these grammars now? Because language syntax rules are specified with the help of grammars. So every statement uh, must be defined in the form of a grammar, and parser verifies the corresponding statement with the grammar specified, so that it is following the same syntax rules specified in the grammar. Otherwise, it produces errors, syntax errors. So therefore, it is important to understand how grammars are used, so that in a later phase you will be able to understand how the design of parsers is performed with the help of these grammars. Okay, so let us begin with the definition of context-free grammar. Any grammar is defined with the help of a four tuple, a quadruple, v, comma, t, comma, p, comma, s, where v is a set of variables, t is a set of terminals, p is a set of productions. This is important. Set of productions which are of the form, uh, say this, a implies alpha, where a belongs to v. That means left side of any production, LHS of any production is a single variable. RHS of any production is a combination of variables or terminals. So zero or more occurrences of variables and terminals. So this is the production rule. Every production must satisfy this rule. Okay, and S is the start variable, which is also a variable, belongs to set of variables. So If you are defining a context-free grammar, it should be set of variables, a set of terminals, a set of productions, and a start variable. So let us see an example. Say this is the production, and this is the alphabet on which this grammar is defined. So what it is saying, S implies ASA or BSB, or this pipe symbol denotes separation of productions. This also means that S implies ASA, S implies BSB, S implies A, S implies B, S implies epsilon. Uh, this is a notation for epsilon. Some people use this. Okay, right. So this represents a context-free grammar as specified in the previous definition. Left side of the grammar, any production contains a single variable, whereas the right side of the production contains any combination of variables and terminals. Small letters are terminals, capital letters are variables. Okay, and this contains only a single variable, which is start variable here. Okay, so if you remember, this grammar represents a set of palindromes generated from the alphabet A comma B. Because epsilon is included, empty string is also allowed here. If you remove that epsilon, it means non-null palindrome. That means at least one symbol must be there in the palindromes. Okay, so this is an example of context-free grammar. And then you need to understand, after defining a grammar, how do you derive a string from a particular grammar? Okay, to verify its validity. Suppose I want to derive a string id plus id star id from a grammar, say e implies e plus e, or e star e, or id. Say that is the grammar. Actually, it is not mentioned here. Imagine that the grammar is e implies e plus e, or E star E, or ID. So there are three productions. So E has three productions. One is E plus E, capital E plus capital E. The second one is capital E star capital E. And the third one is ID. ID is an identifier. Suppose you want to derive this string, ID plus ID star ID. So what will be done? Right. Now let us understand how this. There are two types of derivations actually: leftmost derivation and rightmost derivation for deriving a string from a given grammar. There are two approaches you can follow. Let us understand LMD first, leftmost derivation. In leftmost derivation, at each step of derivation, the leftmost variable is replaced by its equivalent production. You can replace with any production, but only the leftmost variable should be replaced. So we'll consider, because the first operation is plus, we will start with E implies E plus C. And because there are two variables on our RHS, you will consider the leftmost variable, this one. In place of this, I will substitute ID, because E implies ID is a valid production, and then plus C is there. Now this contains only one variable, and that becomes leftmost variable. So ID plus E, this is replaced by E star E, because I want to produce ID star ID. So E is replaced by E star E. And then in the next step, the leftmost E is replaced with ID. And in the last step, the only remained variable, capital E, is replaced with ID. So this is how a string can be derived from a particular grammar. If you observe, in each step of the derivation, only the leftmost variable in the RHS string is replaced with some production. Okay, and rightmost derivation is quite opposite to that, where in each step of the derivation, rightmost variable is replaced with the corresponding productions. Okay, suppose I want to derive the same string, and I'll begin with the E implies E plus E, and then because the rightmost production I must replace, so E implies E plus E is there. I'll replace this rightmost variable with E star E. Now it contains three variables, so the rightmost variable is now replaced with ID, and then next rightmost variable is replaced with ID. And finally, there is only one variable remain that will be replaced by id. That is how you can reproduce id plus id star id using which method? Rightmost derivation. So you can derive a string from a given grammar with the help of either leftmost derivation or rightmost derivation. And the important topic here is, what is a parse tree? It's very easy to understand parse trees here. Parse tree is a representation of derivation process, either from LMD or from RMD, deriving a particular string from a grammar. You can represent it in the form of a tree, which is called as parse tree, or another name for this is syntax tree. You can call this as syntax tree. Suppose I want to derive 5 plus 1 into 12. So this is what I want to derive. Then let us say first I have used E implies E plus C, which will be represented like this. For every symbol, there must be a path represented properly. And then the first E is replaced with the 5. Plus is same, it is the terminal. And second rightmost E is replaced with E star E. And finally, this E is replaced with 1. And the last E is replaced with 1. If you observe this parse tree carefully, all the intermediate nodes are variables. All the intermediate nodes are variables, whereas the terminals are, these are leaves. The leaves are terminals. And what is the string represented by this parse tree? Read from left to right, all the terminals, all the leaves. So starting from leftmost leaf, that is 5, plus next leaf is plus, and then 1 into 12. So the string is 5 plus 1 into 12. So this represents the derivation of 5 plus 1 into 12 from the grammar. E implies E plus E or E star E or identifies. Okay, so that is what a parse tree is. Then the most important topic to understand is, what is an ambiguous grammar? A grammar is said to be ambiguous grammar if there are more than one derivation trees possible for deriving the same string from a particular grammar. So if you want to derive a string, if there are more than one ways of deriving the same string from the grammar, then it means the grammar is ambiguous. This is the grammar. The grammar is said to be ambiguous. To prove any grammar as ambiguous, what you need to do is, you need to identify an appropriate string that will result in producing two different parse trees. Okay, so let us understand this with an example. Suppose I want to produce id plus id star id with the help of this grammar. So I'll begin with E implies E plus E here, and then this E is replaced by ID, this is replaced by ID, and finally this is replaced by ID. This is one possible way of deriving ID plus ID into ID. But then you can start with E into E, which is contrary to this. So E into E, therefore this E must be replaced with E plus E because you have a plus before multiplication. So before multiplication, it should be a plus operation, E plus E. And finally, this is replaced by ID, this is replaced by ID, and this is replaced by ID. If you observe, the structure of this parse tree is different from the structure of this parse tree. That means for deriving the same string, this tree is representing ID plus ID into ID, and this tree is also representing ID plus ID into ID. Both the trees, both the parse trees are representing the same string, ID plus ID into ID, which means there are more than one parse trees possible for deriving the same string from this grammar. Therefore, what we can say, this grammar is ambiguous grammar. Okay, and this is an exercise for you. Note down these two examples and try to prove that the grammar is ambiguous. So what is your task? What you need to do to prove any grammar is ambiguous? You need to identify an appropriate string from this grammar so that it produces two different parse trees for deriving from this grammar. This E, even though it is written as E, represents epsilon. Okay, here also this is epsilon, right? So try to solve these two problems. Uh, I hope you solved these two problems already in your formal languages and automata theory. These topics are same uh, as your fourth unit, probably third unit or fourth unit. You will see these examples in your flat notes also. You can refer to it. Then how to eliminate ambiguity? Because when you are designing parsers, it is compulsory that the corresponding grammar for which you are designing a parser should not contain any ambiguity. Okay? It should not contain any ambiguity. Therefore, elimination of ambiguity is an important task. So let us understand how to eliminate this. The process is very simple. You are going to replace the second occurrence of variables, same variables, with a new variable, and the same process will be repeated until all the second occurrence of variables are replaced properly. Okay, and this replacement process begins with the least precedence production. So in this grammar, the least precedence production is E plus C. So we'll begin with E implies E plus C, and we replace that second occurrence of capital E with a new variable T. How this is the way. E implies E plus T or T, because this E is replaced by T. That means E also represents T. Okay. So E implies E plus T or T. And then onwards, every other production after this should be replaced with T only. That means E star E now becomes T star T. T implies T star T. Okay. And again the same process. In E implies E plus C, the second occurrence of E is replaced with a variable T. Now in this, uh, T implies T star T, the second occurrence of T is replaced with another variable. Let us say it is F, which means T implies T star F or F. And finally, this is actually E implies ID, which is represented as E is replaced by T, so it is T implies ID. And because we selected F for T, T is replaced by F, producing F implies ID. So altogether, E implies E plus T or T, T implies T star F or F, F implies ID. These three becomes the unambiguous grammar. So there is no ambiguity now. You can use this grammar to produce the same string to check whether ambiguity is also is there in the grammar or not. Okay, you can check it. That is an exercise left for you. I think this is also available in your notebook. You can refer to your flat notes. But please, all of you do this task to verify whether this grammar now is ambiguous or not by using the same string, that is id plus id star id. Try to produce two different parse trees for deriving this string. Okay, if you are not able to get two different parse trees, it means there is no ambiguity. Okay, right. Another important concept that you should understand uh, about grammars is left recursion. What is left recursion? A grammar is said to be left recursive grammar if at least one production in the grammar is of the form A implies A alpha or beta. So what is the speciality of this production? If you see, the variable on LHS is capital A, and RHS production is beginning with capital A again. That means the variable on LHS, if it is the first symbol on production on RHS, then it means there is a left recursion in the grammar. Okay, and this beta is actually uh, any production that does not start with A. It can be any combination of variables and terminals. Even it may contain a variable also, but it should not be capital A. Okay, so that is what beta is. Beta is any combination of variables and terminals that does not start with capital A. That is from that is with the left hand side variable. Okay. Now let us understand this. E implies E plus T or T is left recursive. Why? Because the LHS variable is capital E, and the production is starting with capital E again on a RHS. Therefore, it is left recursive. Okay. Then how to eliminate left recursion? Because it is important to remove left recursion if you want to design a parser for a particular given grammar. The grammar should not contain left recursion also. Therefore, it is important to understand this. Now, let us see. Uh, this is the production which contains left recursion. Then to remove left recursion from this grammar, we have to replace this set of productions with these productions. What is it saying? A implies beta A dash. So use this beta followed by a dash. This is a new variable. You can use any name here. I'm just using a dash to represent that. It's a new variable, new replacement for capital A. Okay. So beta a dash. What is beta? Beta is the remaining productions that does not start with capital A. And the a dash implies alpha a dash. What is alpha? The string that is followed by capital A here. So alpha a dash or epsilon. This is epsilon. Okay. So you can eliminate the left recursion from this production with the help of these productions. Right. Now to understand this, let us say I'll consider E implies E plus T or T again. This can be transformed into without left recursion like this. So how to do it? This is A, this plus T is alpha or T is beta. So what it is saying? Beta A dash. What is beta here? T. T A dash. A dash is E dash. And E dash implies alpha. Alpha is plus T. So plus T, E dash followed by epsilon. Similarly, you perform the same task on this because this also contains left recursion. You apply the same rule on this, and finally you will get 2 here, 2 for this, and this is not containing any left recursion, so it will remain same. Okay, so overall these 3 productions will be converted into 5 productions. So you do the remaining task, convert this into a grammar which does not contain left recursion. Okay. And another important concept that you should know is left factoring. Left factoring is not allowed in the grammar uh, for designing parsers for it. When you need to left factor is if any production contains a common prefix, let us say common prefix for the set of productions on RHS. So if you observe this example, alpha beta 1 or alpha beta 2, both the productions contain alpha as the prefix. So there is a common prefix over here. Therefore, you need to left factor this production uh, as take this alpha as common and introduce a new variable in place of beta 1 or beta 2 like this. A implies alpha A dash, and then A dash represents beta 1 or beta 2. Now, you cannot perform left factoring on this. This is called left factored grammar. Okay, left factored grammar. So this is the same example. A implies A alpha 1, A alpha 2, A alpha 3. There are 3 common prefixes over here. So take that A out of it and represent a new variable in place of alpha 1, alpha 2, alpha 3, something like this. So A implies A dash, and A dash derives alpha 1, alpha 2, alpha 3. Okay. So these are common prefixes, the grammar with common prefixes. After performing left factoring, this is called a left factored grammar. Okay. Okay, with the help of these fundamentals, knowing now how to eliminate ambiguity, how to eliminate left recursion, how to convert the common prefixes into left factor grammar, now we are ready to design any type of parser. So in our next class we will begin uh, the design of parsers. We'll begin with the classification of several types of parsers that we can design, and then we will discuss about designing each one of them one by one. In second unit, we will be designing probably three types of parsers, and then in third unit, we will perform design of remaining parsers, the advanced parsers in third unit. Okay, so our next task is going to be design of parsers only. Okay, so that's all for today. See you again in our next class.